Hello, welcome back. In this video, we're going to cover some of the existing approaches to identifying important inputs, and we're also going to talk about their limitations. And we're also going to give a high-level intuition for what makes DeepLIFT different. Perhaps the most intuitive approach to understanding which inputs are important for a given prediction is a perturbation-based approach. The idea of approaches like this is to make a perturbation at a particular position and observe the change in the output. This is repeated for all possible perturbations at all possible positions. There are some drawbacks to this approach, but perhaps the most obvious is computational efficiency. Every time you make a perturbation, you have to recompute the output. When your input is very large, this can rapidly become prohibitive. Another perhaps most subtle problem is susceptibility to saturation effects. Consider the simple network shown. There's a hidden unit h, which computes max of 0, 1 minus I1 minus I2, and there's the output neuron y, which is 1 minus h. The functions computed by h and y are also shown on the left. So let's take a look at the point where I1 is equal to 1 and I2 is equal to 1. Here the output of the network is 1. If at this point I individually zero out an input, I will not observe a change in the output. This may mislead the user into thinking neither input is relevant for the prediction. Saturation effects like this are not uncommon in real life. For example, in genomics, through the process of evolution, our genomes have evolved redundancy specifically so that we can survive small mutations to our genomes if they crop up by chance. For example, if you're studying a protein binding site, often you'll find multiple redundant instances of viable binding locations for the protein, specifically so that if one of those instances is mutated, there are other instances that can recover the binding. An alternative family of approaches that addresses the computational inefficiency of perturbation-based approaches are backpropagation-based approaches. Here, you start with a particular output and assign importance scores to the neurons in the layer immediately below, depending on the particular function connecting those two layers. You then repeat the process, backing down through the layers until you reach the input. Note that importance scores can be negative. For example, if the purple neuron on the left looked for the pattern AGATA and it saw a C in the first position, and assuming that purple neuron contributed positively to the output, the C would get a negative score because it contributes negatively to the firing of that neuron. The reason such approaches are more efficient than perturbation-based approaches is that in a single backward pass you get importance scores for all the positions in the input. There are a number of existing backpropagation-based approaches, but they are all fundamentally either related to or based on taking the gradients, and because of this they also fail for very similar reasons. This led us to develop DeepLIFT, which is also a backpropagation-based approach, but which takes a fundamentally different perspective on how to propagate the importance scores. Why are gradients problematic? Let's revisit the saturation example. Note that when y is equal to 1, the gradient of y with respect to both I1 and I2 is 0. In fact, this is what the word saturation means. So using the gradients would still flag neither I1 nor I2 as relevant for y. How does DeepLIFT get around this? At a very high level, DeepLIFT relies on the concept of a difference from a reference activation, where the reference activation is the activation that a neuron has when presented with the reference or neutral input. And we'll talk a lot more about that when we dive into the details of DeepLIFT. But for now, assume that the reference for both I1 and I2 is 0. Note that when both I1 and I2 are 0, the activation of H is 1 due to the positive bias term. Now, when we look at the point where I1 plus I2 is 2, the difference from reference is negative 1, even though the gradient locally is 0. This is the information that DeepLIFT uses to propagate importance even when the gradient is 0. One nice thing about the DeepLIFT approach is that it generalizes to all activations. Consider a sigmoid and imagine the reference input is 0. When the input is very large, the gradient is near 0, but the difference from reference would be positive 0.5, even though the gradient has saturated. Sigmoid functions are often used as gating units in recurrent neural networks, so a DeepLIFT-based approach could prove especially useful in such contexts. A second failure mode of gradients occurs when the net is describing thresholded relationships. An example from genomics would be a neuron that only fires when it sees a sufficiently good match to the binding site of a particular protein. So consider the function shown that is computing max of 0, input minus 10, so 10 is our threshold. If we look at the gradients here, we see that they are 0 when the input is less than 10 and 1 otherwise. Now, the gradient stays at 1 regardless of how strong the input is, and a simple fix to that is to use gradient times delta input, and if the delta is measured with respect to 0, this just becomes gradient times input. So this is desirable because at least with stronger inputs you're getting a stronger response, but there is still a sudden jump when the input is 10. In fact, what happens is that when the input is just less than 10, gradient times input assigns 0 contribution to the input and 0 contribution to the bias term, that is negative 10. And when the input is 10, gradient times input assigns an importance that's a contribution of positive 10 to the input and negative 10 to the bias term to make up the difference. We argue that going from a contribution of 0 to a contribution of negative 10 over an infinitesimal increase is misleading, especially if you are a bias term and you're kind of always there. DeepLIFT, by contrast, is based on the actual difference from reference and not the gradient, and thus it never has to assign contribution scores to bias terms and instead shows a gradual increase in importance as long as the input has surpassed the threshold. Now, to be fair, there is another strategy that can be used to tackle the saturation and thresholding problems. It's the method of integrated gradients proposed by Sundararajan et al. The basic idea is to pick some starting value, which is not unlike a reference, and scale the input up linearly from this reference to its actual value, and compute the gradients along the way. Specifically, do gradient times delta input at each step, which is like computing an integral. Because delta input will be the same for every step as you are doing the scaling up linearly, this turns out to just be the same as computing the average gradient over all steps and multiplying by the total delta input. This approach addresses the saturation and thresholding problems, however, there are 2 caveats. First, doing the numerical integral adds computational overhead. And second, does it always give a good answer? So consider the network shown, which is computing the function y is equal to I1 minus max of 0, I1 minus I2. When I2 is less than I1, H1 is positive, meaning H2 is equal to I1 minus I2, and y becomes I2. Similarly, when I2 is greater than I1, H1 is negative, so H2 is 0, and y is just I1. In other words, y is min of I1, I2. We find that the network learns functions like this when it is trying to represent an AND relationship, that is, both I1 and I2 need to be high in order for y to be high. An example from genomics is that both protein A and protein B may need to be present in order for the region to become active. Gradient-based approaches would assign all importance either exclusively to I1 or exclusively to I2, depending on which one is smaller, because for the function min of I1, I2, the gradient is going to be 0 on whichever input is larger. This can give a misleading impression because it misses the fact that both I1 and I2 are relevant for the AND. This problem unfortunately doesn't go away if you use integrated gradients instead of just gradients. Consider what happens when you use a reference of I1 is equal to 0 and I2 is equal to 0, and in this case assume I1 is greater than I2. If you scale the inputs up linearly from 0, 0 to I1, I2, you're still going to have a gradient of 0 on I1 all the way. So integrated gradients would still assign 0 importance to I1. Using DeepLIFT, we can actually fix this problem, and the intuition there is we give a separate treatment to positive and negative terms. But to really understand how, we're going to have to get into the details of the DeepLIFT method, which we will do in the next video.